Let me do a ping and I'll show you how this ICMP works together with this trace route. Let me open up my Wireshark. So I'm going to quit. Open up the Wireshark. I'm going to capture my Wi-Fi traffic. So if I do a trace route, simultaneously, if I open my Wireshark here, if I put ICMP, let me put IP dot address equals 8.8.8.8. This all predefined rules, the color codes the Wireshark uses to distinguish the traffic. Okay, so if you look at here, this is my first packet. It's going to the gateway, this 192.168.0.1 from my source here. This is my source. And this is the destination. And it is using ICMP. So traceroute uses ICMP in Windows. As I told, it differs. And this particular router, right? It's replying back to my source. And what it says, the TTL value exceeded. It's using ICMP. So yeah, as I told you, we have a separate class for TTL. So for every hop, you see this time to leave exceeded. So it will come back to the source. And if you see every time the source is doing again and again, my source is sending a packet back to the destination for all my TTL. If I give an IP address 10.232.0.1, so this particular packet 10.0. This particular destination, it says, hey, your TTL exceeded. I am going to send this back to your destination. This is your source PC. This is how it finds every destination. So it puts a TTL and so first value, it's put a TTL value 1 and it sends to google.com, but it reaches here, my 192.168.0.1 from my PC, that is .104 with TTL of 1. It's going to decrement the value of TTL of 1 minus 1 is 0, and it will send back again to my source, .104. Now it says, okay, I cannot reach this with TTL value of 1. I'm going to increase this. This is by design by the traceroute works. So it's going to put the TTL value of 2, and it's going to send to the same destination, and it's going to reach the first hop and the second hop. Once it reaches the second hop, now my TTL becomes 1 when it reaches here, because it sends with 2. The first hop decremented by 1, and the second hop again it decrement the value by 1, and it becomes 0 and send it back to my PC. The same process happens until here. So for every time it fails, time to leave exceeded, it's going to increase the TTL value. So here the TTL value is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it would the final TTL value from this particular PC, if it sends with TTL of 11, So it becomes in the 11th hop, it becomes 0, and I'll get to know about the destination till I reach. This is how the trace route works. So if you calculate that, somebody asked a question yesterday, it's a 12 hop away. So there's a maximum hop of 30. So this is how the TTL works here. So this, you can practice this and you will get to know how exactly the TTL works. And in the lab, we'll do this TTL in the future class. So this is all about the layer 3 headers. So the other values we'll be looking at, we'll discuss more, but the main key components, source IP, destination IP, source IP, destination IP, and what is the IP version we are using, and what is protocol ID is something that's related to what is my next protocol. Is it a TCP or UDP? So all about the protocol numbers we see there. And differentiated services is about QoS. This is applicable for both layer 2 and layer 3. We'll see that in the labs in the upcoming classes. But here the differentiated services we see there. What is differentiated services? And we'll discuss about IP identification. So I'll show the Wireshark, that would be easier for you to follow. When I open a Wireshark here, so let's take IP packet. Let me take this IP packet. As I told you, we use checksum, right? Here, if you see this checksum, it uses a checksum status. So checksum says it's correct and it's good. And we got this TTL value here. Time to leave. The protocol, what we are using is a ping. We are doing a ping in ICMP, and the protocol number is 1. And you got your checksum field, your protocol, your TTL. And IP flags, we'll discuss about that. IP flags, we got 2 values. One is fragmentation. That is something I told you, if you're sending your jumbo frames, then this particular packet will be showing up how many packets it's been fragmented. We'll show that. I'll show you that in the lab, how we'll do this fragmentation. If you see here, we done the fragmentation, and we saw the fragmentation is increasing on the switch. So it fragmented 10 packets are fragmented here, because I'm sending a packet with a payload of 1600, it has to be 1500. This is fragmentation. And if you capture this particular packet, and you will actually see the fragmented data that's showing up here. The lab will look into it, but just want to show you what is fragmentation field set. The IP identification is the key thing. IP identification is, say, for example, if I open this Wireshark capture, you'll understand better. If I give an ICMP here, this is something I would say, IP identification is stamping your packet. Every packet, you're stamping something like, hey, I am giving a number something like 3761. This is one particular conversation. If I send one ICMP request, so there are 4 ICMP requests by default. So for every ICMP request, I'll distinguish every ICMP request with the identification number. It is IP identification number. So example, if I take the IP address, let me filter out the value. IP dot address equals 20,001. If I do this, if I drag, I have added this identification number here. We do right click apply as a column, you will get this field right away here. If you look at this, this is my first ICMP request. For this ICMP request, I get a reply. And if you see, this identification number remains the same. Okay, it's for this. This is the first ICMP request. This is definitely not possible without the identification. So we never use this identification. If you remove this identification, how it looks. Remove this column. I don't know anything about that. It's just, I can see this is an ICMP. No more information about that. But if I make this as a column, there exactly I see this is first ICMP request, and this is my second ICMP request. Why I cannot track this? If you see, this is the first ICMP request, and this is my second ICMP request, third, fourth, and it is a random number that's generated by the PC. This is a quick identification. If I do a continuous ping to the destination, where I can find, okay, where exactly my ICMP is dropping, which particular ICMP packet is dropped, right? Otherwise, we have no clue. Somewhere it is dropped, but where exactly it dropped. So that gives you more insights about this ICMP with this IP identification. That's very helpful for when you do a troubleshooting. So this is one common, the simple script. I'll give you the script. This is if you do a continuous ping with 5,000 packets, it keeps running. And if you capture the same thing here, it's going to show you where exactly I'm dropping the packets. So if I do ICMP, if I do IP dot address for the Google DNS, so it's keep running, right? So if I stop this particular capture, so there exactly my ping dropped. And with this identification number, you can go through that. You don't want to look at this hexadecimal value. You can always key in about only this. If you look at this particular source, 70.14.243.242, if you compare the identification number, this is for every TTL exceed, you see a different identification number. So it means that this is an every individual ICMP request. So you can find out, okay, where exactly my packet dropped. So this particular script, it will give you a value along with your date and time, exactly where exactly you're dropping your packet. You can run this in the Windows PowerShell, and simultaneously with Wireshark, it will give you more insight about where exactly the problem is and when exactly it happened. This might be very helpful when you do a troubleshooting with a server, and if you're dropping a packet in a particular server, then you can track with IP identification. So for now, let me pause the So if you actually see this capture, that's my capture. It says no response seen.
Yep.
Warning is it exceeded the MTU. If you want to check the default MTU for my Windows, this is a command where you can check.
Yep.
And this is maximum is 1500 bytes. And now I'm sending a packet with the length of 1600 and it's dropping the packet I cannot make reach to the destination.
Okay.
Ajay, just
no
one
response.
question. You were showing that a ping to that global DNS, right? 8.8.8.
That's right. Yeah.
You are saying like 116. That is the value you have seen for the TTL, right? Actually, that is the TTL for the destination server, right?
No, you got it. What is TTL? I mean, we discussed about TTL, right? How TTL works. TTL is always decremented on every hop.
Yeah, I got that
So,
point. Because
so-
when you're talking, yeah, go ahead. Please.
Yeah, what's your name, please?
Shine.
Sorry?
Shine. Yes.
Okay.
So when you are talking about ping, there will be echo request and echo reply will be there. Okay, we
Yeah.
have sent the echo request. During the echo request only, we are making that TTL to 128, right?
That is using ICMP. It is using ICMP. The traceroute uses the mechanism of decrementing TTL. So TTL, generally what happens, even if you do a ping or a traceroute, both use the same ICMP. So for every hop, the TTL will be decremented. Example, if this is a Windows PC, right? This is a Windows PC. So if I do a ping to 8.8.8, so what happens in the background? So here it uses ICMP protocol. So I'm going to send an ICMP request. So inside the ICMP request, my TTL value will be 128.
That is right. Yes.
Right. Once I reach to the next hop, so it becomes TTL. It will check, okay, it is 128 and I'll make it as 127 and send it back to here. Sorry, this is for a trace route. So it becomes 127 and then it goes with a TTL value of 127 from this hop to the next hop. So now my TTL value become 126 in the same way until I reach my destination. Example, in the TTL value is 117 and now I reached. So if you subtract the actual value of 128 and 117, what is the remaining value you get? Example, something like 10.
That is for the echo
number
request,
10.
right?
Don't confuse about that. So for every hop, the TTL will be decremented. That's not for ICMP request and reply. You got it what I'm saying? ICMP, it uses 4 packets, 4 consecutive packets, 4 probe packets. That is for 4 ICMP requests. For my 4 ICMP requests, I should receive 4 ICMP reply. That's it. TTL is the number of hop it takes. ICMP and TTL both are not related. But since we do a ping and it uses an ICMP and it sends a packet with TTL, you got it. You don't mix up with both. ICMP is different. TTL is different. TTL decides your number of hops. ICMP decides, is it for your ping request, I'm getting a ping reply back. ICMP is different. TTL is different.
So if we are doing a ping within this TTL, if we are not reaching the destination server, we will get a message, right?
Yeah, that is a one-to-one communication, right? Yeah, definitely. Yeah.
And can you explain about that trace route, the decremental behavior of the TTL?
No, yeah, we have a separate class for it. So I'll go with every single hop and how this TTL exceeded message happens, because for Windows PC
Both
it uses
with
ICMP.
ping as well as trace route, there is a class.
For a ping and trace route, for ping, that's basic, but trace route we have a class, and if needed, yeah, we will have a session for ICMP also, no problem.
Okay, thank you.
No problem.
So Arjun sir, what is the difference between the MTU and MSS that you were telling earlier?
MTU is a layer 2. Okay, MTU is a layer 2 where
payload. Yeah.
Payload. 1 minute.
1500 bytes. So what is the MSS? Is it layer 4?
It's layer 4. That's right. Maximum segment size. Yes.
So both of them are relevant. Both of them are relevant.
No, both are not. No, both are not relevant. Both are different. That is layer 4, and this is layer 2.
I have a question which is not related to this class. Where this duplex and all coming in the OSI layer?
Duplex is more with your layer 1, right?
Layer 1 only, yes.
Half duplex, full duplex, yeah.
Okay.
One-way communication and two-way.
Layer one.
Arjun, won't MTU will come under layer 3?
No, MTU comes only
So
with
there is
layer
also an
2.
IP MTU, right?
With packet
We
drive.
can
Yeah.
set the MTU on the interface and also on the globally, right?
No, that is actually a payload when I set it this, but that not applied to, see that is the amount of data what that the particular frame that's carrying. That
Mhm.
decides your MTU.
Arjun, just still,
IP packet is different. Yeah.
yeah, still I'm not clear because TTL I understand, I totally understand it will decrement hop by hop. That part I got it. But when it is coming to ICMP, okay, as I still already told, it will be having echo request and echo reply. Okay, I'm the client. Okay, I'll be sending the echo request. At the end of the day, it's a ICMP connection, right? So when I'm sending the echo request, if I'm Windows machine, hopefully I believe it is 128, we will make the TTL value to 128 and it will reduce every hop. It will reach the destination. For example, it is 11 hops away. It will be 170. Okay. Now the echo request has reached the server. The server has to send the echo reply back. Okay. While it is trying to generate the packet, okay, it won't take that TTL, right? It will generate the TTL with his operating system and it will send back to me.
Okay.
Okay, because while I'm checking the capture, because see TTL I understand, as I already told, but this packet while I'm doing the capture for the echo request and echo reply, I could see I could see the difference because I'm sending 128. I could for the echo request and echo reply, I could see two different TTL. Usually it should be the case, but you were saying like there is no TTL coming to the picture. That's why I was getting confused.
No, TTL is purely decided by the source. What is the capture you're talking about? Let me see. What is the capture you have confusion? Let me see.
Yeah. Sure.
What is the capture you're talking about, please?
I think that's a capture on my end.
Okay.
This one.
One minute. Yeah. What is the, what is your name? Sorry. Was
Shine.
talking to Shine.
Yes.
See, this is, say, TTL, you get two TTL values. See, I'll tell you. So this is source. This is destination. This is a Linux. This is Windows. So I calculate all with TTL value 128. And you do the calculation with TTL 64. Right? So for this particular TTL calculation, that happens between, this is a peer-to-peer, right? ICMP is a peer-to-peer. In the trace route, that is different. In the ICMP, it is something, hey, are you active? I am sending 4 ICMP requests. For the 4 ICMP request, I should get 4 ICMP reply. So my TTL is decided upon this ICMP and my TTL that's been set in the beginning. So here there is no mismatch about TTL. If, for example, if you go back to the ping, this is pretty straightforward, right? So if I do a ping to 888, so here it says it is the TTL is decrementing because what do you think? This communication between the source and destination, it's a peer-to-peer communication. 8.8 is responding to my PC.
That's right.
This
So,
TTL, one minute. Let me, I'll finish it. Otherwise, I cannot explain you. See, if this is something, this TTL, if you minus this 128 with 116, example, I'm saying. So what is the value you get here? 12. So there is 12 routers in the middle. And then in the 12th hop, I am reaching this destination. That's the meaning of this TTL.
Okay, can I share my screen?
Yeah.
Possible, but let me see. Share. I think host is disabled.
TTL will be calculated only based on the route switch, right?
That is it, based on the number of hops, how many hops I take to reach the destination. That decides the TTL.
So when the client, okay, the source sending a ping request, it will calculate the TTL as per its operating system. And when the destination sending the ICMP echo reply, will there be any TTL for that also generated by the back target?
Yeah, exactly. It will send back, right?
Okay, that also has a TTL, right?
Yeah, that also has TTL. For
Okay.
every host in a network has a TTL.
One
Where it
more.
wants to send a packet, yeah. I cannot see.
So, Arjun sir, TTL will decrease only by layer 3 device, I mean gateway only. Let's suppose any like 2 or 3 switches are also in between the traffic. So
Sorry, what is the question?
let's suppose I am pinging to one of the destination. Okay. So my question is that, so TTL is only decreased by gateway, like how many gateways are in between the device, or
That's exactly how many IPs in the middle that
Mhm.
does the routing, that actually look at the TTL, and your TTL will be decremented accordingly.
okay.
Suppose if packet enters a MPLS network, there it won't be decremented, right?
Sorry?
If our packet is going through certain MPLS network, in that case, it won't be decrementing the TTL, right?
I think you have to do some tweaks with MPLS for that.
Okay.
Then, yeah, that will not be. There is some tweaks it has to do with MPLS.
Yes, sir, that you need to do, ignore the MTU. So there is a thing, there is a command in MPLS that you can use, and it ignores the MTU. So when you send the packet and it traverses the ISP MPLS core, then the attacker who is attacking it, he will not know that, okay, how many hops the packet has traversed, and it will save the MPLS core from any attack through flooding or anything like that.
Yeah.
Gee.
And Shine or someone, he asked a question, right? So if you see this, my source is the public IP, and if I see the different TTL, it's because its own TTL. See, it is 64, and 64 minus 45, what is the value? So how it will reach my destination from 64 to 45 is something, how much it is? 14.5. I'm not with my. So
Can you just search for IC?
example I'm saying, see here, if you reduce something like 14 minus 5, right? 459.
19.
Yeah, 19. So it takes 19 hops to reach my destination. Example I'm saying. So one minute, yeah, let me finish. So this TTL is decrementing based on the source. So it sent a TTL with 65, and it has to go through these many hops, 19 hops, to reach my destination. And my TTL is, it's showing my TTL is, decrementing, and I have a route to your destination, and this is the number of hops I take to reach your destination. That's the meaning of TTL.
Yes,
and this is purely on layer 3 header.
Exactly. In this case, the TTL is set by that 134.224.140.99 host, correct?
That's exactly.
Can we just go back to ICMP packets?
This is ICMP or UDP. And let me open up the ICMP. Yeah.
There is no ICMP. Okay, can you just take one request and reply? Just
ICMP request and reply.
Yeah.
Yeah, this is all request, and I didn't get any reply for this particular pack capture. Let me go back to one more capture. This is okay. Both are same. Yeah, both are same. I have to do a capture again. It's my Wireshark. Yeah, tell me. Let's take a capture. Yeah.
Yeah. Now, can you just filter with ICMP?
Okay.
Can you just take one ICMP echo request and reply? You have so many filters.
Yeah, this is ICMP request and reply.
Yeah. The first request, we will take two requests. Okay, one is one request and reply. Okay, the request is being initiated from your PC to the Google DNS.
Yes.
Okay, if you look at that TTL, that is 128. Okay, now the return packet, that is reply packet, that is being initiated from the Google DNS, correct?
Yes, that's right.
So the second packet, this field TTL field is set by the DNS, right?
Yeah, it's all ICMP is used here.
Yeah, the TTL value, it is for the echo reply, the TTL value is set by the Google DNS server, right?
That's right. Yes.
It's clear now.
Yeah, that's what I'm saying. See, this
Because,
is
no,
you can.
Why I asked, while you were just trying to ping from CMD, you were saying the TTL is set by the value we were seeing 116, right? I'm not sure whether it might be by mistake, but you are saying the TTL that 116, it was from the machine. That is what the question, I got confused back, because actually the TTL for the return packet, it is set by the DNS server.
Yeah, whomsoever is replying for ICMP request, it has to reply back. So it has to add its own TTL. That's what I told. Even in the chat, it's decided by the source.
Because I just heard it is the client. That is the reason that I got confused.
No, 116 represents that how many hopes that has reached and getting the reply.
That's right.
Now, I think we have three possibilities here, right? Now, either it can be started from 128 or it can be started from 255, correct?
Yeah, that is by looking at the values, we will get to know, is it 128 or 255? Here, you don't see anything with 255, but if you capture something with Cisco appliances, you would see something like 255 here.
I'm just talking about a 116, because either the packet which might have generated with the TTL value 128 and it has passed 12 hops, so now the value is 116, or else the packet TTL value, it might have started with the 255 and it might have traveled almost 100 plus hops, right?
100 plus is not practically possible in the real network. Maximum it can be 30. Okay. Maximum is 30. Maximum is 30.
Yeah, now it's clear.
Yeah, you don't see something like, if you got 64 with TTL 64 and I see a TTL 3 and I got a response back. That's really, the number of hops is too high, but I never seen that in the practical scenarios where I see the TTL maximum, it could be below 30.
Okay.
Sir, one question, sir. Sorry to interrupt you. Sir, ये जो frame था, sir, layer 2 frame, right? Okay. We said that the maximum size can be 1500 bytes. Okay, sir.
What is that frame size? No, I'm talking not about.
So MTU, sir. The size.
MTU. Yeah.
So, sir, MTU, we said that it will be on layer 2, right?
Yes.
So layer 2 frame size will be 1500 or 1518 to be very exact, right? So sir, ये जो packet होगा, packet layer 3 पर या layer 4 पर जो segment होगी, sir, इसका भी size, this cannot exceed 1500. Is that correct?
That MTU that sits back only with layer 2. That never goes back to layer 3 or 4.
जी.
See, when the packet arrives to layer 2 with all this encapsulated payload, that is something like it should not exceed the amount of data. So that's how they have designed. So that's why we are reducing the MSS. If the question is something, the MSS, why we are reducing for GRE is because we are adding that extra header that makes the MTU bigger. So for that, I'm reducing. So the MTU, you can say you are sending a parcel and your parcel limit is something like a 5 kg. And you cannot send more than that. So that is the total amount of data that can be carried in the network. That's it. So if you make some changes with your layer 4, so you have to change your maximum segment size, because the segment length, if it exceeds and if it is spoiling the MTU size, and if it is increasing the MTU size, then it is a problem, right?
All right. Okay.
You got it?
So,
Hi,
so we,
Arjun.
so we need to adjust such a way that when the packet, after passing from layer 4 to layer 3 to layer 2, it does not exceed more than 1500 bytes.
Yeah, MTU should not increase. Yes.
Okay. All right. Okay. Okay. Thank
Hi,
you.
Arjun. This is Kavi here. Actually, I have a question with regards and the topic what we are seeing. You said the maximum MTU is 1500. On this, we have IP header of 20 bytes and then a TCP header of 20 bytes. And you said the data link will be 14 bytes, right? So all this will be reduced. All this will be minused with the 1500, and the remaining only the data will be sent in the packet. Is it correct?
No. What is your question? Can you
No,
repeat?
the maximum load that packet can take it. Let's exclude the TCP header 20 bytes and the IP header 20 bytes, and you said the data link frames will be 14 bytes, right? So all this will be reduced. The maximum the data that packet can take is 1500 minus this 3 value. Is it correct?
That's correct. If it is exceeding, your end appliances should fragment the data. If it is coming with a bigger MTUs, it should fragment the data. See, if you have what I'm saying, see, example, if you got 2 different MTU like this between source and destination, I'll tell you.
Okay.
It is going to terminate the connection. The MTU mismatch should not happen. So if you're sending a packet here, if your MTU is same here, there is some device that is connected here and you have configured this particular port as a server, there you got your jumbo frames. But what if this sends to your appliance in the next hop? So it is going to fragment this data and send it to the next device. So the MTU has to match. So you have to do exact MTU matching that should happen in both ends. But this is all the default behavior I'm talking about. This is the default behavior, and you can check in the device. That's how the MTU is configured by default. I'm talking about the general scenario.
Yeah, that is correct. But in terms of data payload, this 54 bytes will be reduced. So the maximum the data is traveled is like 1446. Correct me if I'm wrong.
That's correct. See, if you see this ping, if you do this with 1600, what happens here? For this is length, and if I send something like instead of 1500, if I'm sending 1800, so I cannot reach.
Yeah, you cannot reach, but the maximum the payload will be in the packet is 1440. 46.
1500 is the MTU.
Yeah, 1500 is the MTU, correct. But again, this TCP and IP payload will be added, right?
See, what happens if you look at this OSI model? This in every layer, this particular payload will be encapsulated and pushed back to the lower layers, right? So when it reaches the layer 2, what I'm saying is, if this MTU is somehow your segment is increasing this MTU and it's going to drop. So here, if I'm sending an IP packet with 1600 bytes, it's not, it's dropping the connection, right? It's not making to 8.8.8 because my MTU on my PC, it's been set to 1500. So that depends. So if you change the MTU and if it can fragment, then you can do it.
So what's happening here is including
one minute. See, this is my Wi-Fi and this is my MTU, and see, this is a number of bytes what I send. And if it is crosses this 1500, it's not happening. If I make it as a length.
Yeah, I understood this point. The maximum it can take is 1500. I understood that, but you draw an diagram. Let's take that and then that let's construct an MTU there. For L2, it will be like 14 bytes will be added. So the maximum MTU is 14 will be minused with the 1500. Correct?
1 minute, you're talking about this MTU, this is 1500. This is a payload. This is a payload. See, this header information is added along with that. If you see the Ethernet type 2 frame, that is 1518 bytes. This 18 bytes is, this is 6 bytes of destination, this 6 bytes of source MAC along with this ether type 2. So altogether, how much? 12 plus 2, 14. That's added with this 1500 bytes and it's sent. And this checksum 4.
Okay, I understood. But you said 1500 is the maximum. So if you see
See,
here,
I'm again saying, see, this is the data payload I am talking about. So this comes under IP, ARP, etc. And so all this data payload.
If I
This is
understand
solved.
what he meant by on
Mhm.
the data payload, it is not complete data. The data has 20 bytes of IP header, 20 bytes of TCP header. So the actual data from top layers, right? It is 1460 plus 20 bytes of TCP, 20 bytes of IP, total 1500, right? So he's saying the original data is 1460. Is it right or wrong? That is what his question is.
What is the original data is what
I mean,
you are saying from
the original ICMP data. I mean, ICMP sends some
payload,
bytes, right?
payload.
It can be the original payload can be maximum 1460 bytes. That is what his question was.
the actual payload is 1460. So what you're telling here, so this is what is this?
That's what 1460, the actual payload
plus TCP header 20 bytes and then the IP header 20 bytes. Is it so? The payload I'm talking about, not this one.
No, I'll go through this and I'll get back to you. Your question, can you repeat it one more time? What is the 1460? What is the value you define? 1460?
Yeah, 1460 is the original payload. It contains the data. Because if you say 1500, again when we go for the layer 3, IP header 20 bytes will be added, and again we go for a TCP header, again 20 bytes will be added.
Yeah, altogether it's the payload. Yeah, that's right. That's right. Altogether, this is all the header. What you see in the left-hand side, this is the header, and this is the payload. For in every layer, this particular payload will be appended with the header values. So altogether, it should not exceed 1500. It can be your TCP, it can be your ARP, it can be your IP payload. That's it doesn't matter, but it should not exceed 1500 by default. It decided here, this particular PC. And this is something in the recipient who can accept the fragmented packets, you can send again. But here it's not accepting my connection. If I make it as 1600, my packets is dropping. You got it. So this is the public network. We have no information about that. We have a lab where we'll do if we increase the MTU, but still I can ping because my switch is fragmenting here. So it is not static, that because how then we can send the jumbo frame? That is not possible, right? You got it what I'm saying?
Yep, I got it. But so along with this data payload 1500, this 14 bytes will be added for the layer 2.
Along with the 1460.
Yeah, along with this data payload is 1500 bytes, right?
Yeah.
Okay, there IP header and TCP header will be added.
Yeah.
Okay, that's I understood. Here if you see the bottom, you can see 1518 bytes. No, at the top. Yeah, here. So yeah.
64 to 1518.
1518. Yeah.
So you mean to say it can exceed 1500?
Yes.
So Kavi, I want to give you some hints here actually. This is Sridharan here. So if you are sending forget about this, the ICMP ping right now, we are sending about the packet load of 146 and then 20 bytes you are adding, that is a question I understand, right? So if you are sending a 5 gig file or a 5 GB file from A to B, how the packet is going to send from A to B?
Is it a question to me? Yeah. It's it will have the data, and then along with this, it will have the TCP header, and then
so
the
it's
IP
going
header.
To packet everything, right?
Yeah,
it's going to packet everything.
Yeah.
So it's going to put the payload your data inside that. So it's going to fragment everything, it's going to just send 1500 bytes in packet A, and then it's going to keep on sending all the packets from A to B and then finish it. That is exactly he's trying to explain
Yeah, I understood.
Your payload,
Sridharan.
yes.
Yeah,
Yes,
I understood.
through the pipe, yes. Yes.
Yeah, I understood.
So what is the question here exactly?
My question is, if you see the payload is 1500 bytes. Okay. If you see, you know, in this 1500, 20 bytes of IP header will be added, and then 20 bytes of TCP header will be added. So the actual data, that 5 GB I'm gonna send it is in one packet. Maximum I can able to send is 1460.
Correct, yes, sir. Yes, that's correct.
You're
yes.
right.
Yeah,
You're
that's
right.
correct.
Right. Okay.
Because the
So,
MSS
like,
is MSS is 40 bytes less than your MTU size. So you take it that way. So if you subtract 40 bytes and it becomes 1460.
Yeah, 1460. I understood now. And
Yeah.
then
So,
if you see is
no, in real time scenario, I will give you one more hint as well. If you think about this jumbo frames, what he is trying to explain is right. The real time scenario, I have like, you know, this is a real time thing happening. Like, you know, I have experience in my career actually, right? So we have a replication, right, between data center A and data center B. Suppose like, you know, it's in Trumbull and then Virginia. You have two data centers and I have my mainframe data big, like, you know, in like, you know, they push a lot of data, replication data from source A to source B. Like, you know, we have a nexus between that and we have a same network in that. Okay. So, we have like, you know, OTV concept at that time actually, and I'm talking about in 2014, something like that actually, right? We have a OTV connect, like, you know, we have same network data centers between that, right? Actually, where like, you know, they couldn't replicate the traffic actually. They are getting like, you know, the connection timeout. When we checked with the vendor, what exactly happened when we check in the Wireshark at that time. Now this was real time happened actually. We taken the Wireshark and then say that like, you know, your source is sending a jumbo frames, which our network is not allowing because the vendor put a dark fiber that's not allowing the data like, you know, jumbo frame. Then we requested like, you know, a vendor, hey, you have to allow the jumbo frames because it's a replication data. If I keep on sending 1500, like, you know, this thing, it's going to take ever, like, you know, it's going to take like, you know, 5 days to complete the replication of 1 day data. So that's where this, like, you know, the payload comes into the picture, jumbo frames, right? Actually, so we set the jumbo frames so they can set maximum limit and then send it across as per the destination and the source agrees. If it has to match, both has to match the same MTU, then they can just send each other actually. So that's where, like, you know, so I'm just giving a real time picture. That is how the data transmit between that and the jumbo frames and the MTU lies actually.
Yeah, exactly.
So
That's
all
it. I am trying to explain the same thing. This MTU has to match, and if you can send how much data, but it has to fragment. It has to do a
yes.
It is not
Right. Like, you know, I just like, you know, we need to take it very simple. This is not something complicated thing actually. So the real time, this is how it occurs actually.
Yeah.
Hello. So in that replication path, okay, all the devices in that path should support jumbo frames, right?
Exactly. That is like, you know, you have a dark fiber that is like a point-to-point link between the data center. Okay, I'll give you that, like, you know, what is in between actually. A dark fiber, like, you know, DRW, that runs between the data center, that is provider given the pipe directly from my nexus to the other side nexus actually. So we have, so the nexus supports the jumbo frames actually,
okay,
right?
both sides are directly supporting
Nexus takes the jumbo
That's
frames
right.
of 9 to 16. So both
Yes.
sides has to match.
Yes, and also, like, you know, the mainframe devices that connected directly to the VPC on this Nexus, right? You know, that supports it. So, like, you know, it's just as long as both side of the mainframe devices are accepting that, it should be fine actually. Even the same applies to the storage as well actually, the replications as well. Like, you know, you connect to the storage switch, the Nexus 5Ks when you have, and then, like, you know, between the data centers. So mainly, like, you know, those jumbo frames comes into the picture of the replication of the data actually in the real-time picture. Other than that, like, you know, you don't touch the MTU on your missions or VMs or anything like that, right? Actually, we don't touch anything like that actually. Okay, we never get into the picture of doing anything crazy like that actually, because it's going to impact everything, right? You know, you can try that, like, you know, in your PC, you have go to the Ethernet card and then, like, you know, check there is an MTU, you can just adjust that, but, like, you know, it's going to give you an impact actually. right?
Yeah,
Until
that's right.
unless nobody does it, like, you know, we'll not get into the picture. This happened only with the replication, guys, in the real time. Actually, this won't affect anything
That's
else.
correct. Okay. Actually, I'm an FI admin. We are the private cloud. We are doing some storage. Okay, storage application.
Okay.
So there
Okay.
we are using jumbo files 9,000. Okay, so it's in the normal scenario we see 5,000 1,500, but in this kind of big data transfer environment, it's used to see jumbo frames.
Exactly. Until unless you inform your provider to achieve that, like, you know, if you're an FI admin, so what, like, you know, you're using a GLB, or like, you know, is it an LTM you're trying to use as FI as a load
Yeah, it's an
balancer?
LTM
Okay.
hosted on new hardware R15 and 100. It's a
Okay.
F5's
Okay.
latest hardware. Okay.
Yeah, I used
It's
to manage
using,
FI also in my environment. We have like a lot of
this
FI,
is
so
a
I work with them.
powerful box actually. It's a newly introduced. It's a R series box. So
Sir,
that
once
Can
again,
we
only
but
proceed
for
to the next
storage
topic?
application.
no, once again, for dark fiber, there is a point-to-point link so that we can able to adjust the MTU size into jumbo packets or something. But if it is goes under the MPLS kind of scenario from data center, from one
Even
data center to another data center, there might be challenges in passing
exactly, you
adjusting
cannot.
this.
Yeah, the same scenario happened. If the dark fiber is cut down, right? Actually, they have an issue today also. Even like, you know, if your OTV can be adjusted, like, you know, or the VXLAN, like, you know, what you call the advanced version of this, right? Actually,
Okay.
as long as the IP reachability, you'll have the same network, like, you know, it can cover this one actually, right? But like, you know, if you're sending across to the normal MPLS or anything other, you cannot expect everything should be like, you know, coming through that actually. And now we are moving into a completely different world actually. So like, you know, you have SD-WAN, right? Actually, so in that, yeah, in that also, like, you know, you have something called, like, you know, the topology changes. You can set a VPN